Okay, so yesterday we talked about all the bad things that happen to the human body as a result of being in zero gravity, which was kind of the prelude to why do we want to be able to make artificial gravity? Well, now we want to look at how do we want to be able to make artificial gravity. Okay, and we kind of talked about this a little bit yesterday. Okay, the way that we do that, using at least the technology we understand and is available and is not magic, okay, is to create a spinning drum. Okay, if that spinning drum is rotating around and around, then there will be inertia for anything on the inside of it wanting to leave the circle tangent to the circle at that point. Because they're on the inside of the drum pushes back against their inertia. They want to leave, so they push on the circle pushes back directly towards the center. It's a centripetal force, okay, and it would feel like the floor on Earth does. Okay, right now I feel the floor pushing back against my feet, okay, because gravity is pulling me into the floor and the floor is pushing back. Artificial gravity is not gravity pulling me into the floor, it's my desire to leave the circle pushing me into the floor. The floor doesn't know the difference. The floor has to push back. It's Newton's third law, okay, and so it does. And so I feel like I have weight, okay, and all the stuff in my body that normally depends on me having weight works, okay. My balance is still partly or still from my ears, okay. I have impact on my muscles and bones and all of that stuff that keeps me healthy, right? This idea has been around for a very long time. It is not a modern idea, okay, well, like this century modern, okay? It has been around since, before the dawn of really the space age, okay? It was kind of part of the development of that. So the idea is fairly straightforward. The engineering of making it work is not, okay? Having one big ship that just rotates would be easy. If the whole thing was a big wheel or a big cylinder, it would be easy. The problem is it's really not great to make a ship that's a big wheel, okay? We have other things that would have to go in the ship, and if there's a part of the ship that rotates, there's a conservation of angular momentum that you'll learn more about in Physics 30 that's kind of to do with Newton's third law and kind of not, okay? But it's, once part of the ship rotates, the rest of the ship is going to want to do something similar to that because there's going to be drag and friction between the parts. Okay? And so you have to have something that's going to kind of counteract that. All right? Unless just the whole ship is going to rotate. Okay? Now, if you just make a ship that's a big wheel and you're trying to go somewhere with it, okay, what are the engines always doing? Yeah, and as long as you're just trying to go forward and all the engines are pointed backward, it doesn't really matter that they're going around in a circle. It's when you start to maneuver that you're going to have problems. Okay? Because if I want to turn, I can't just fire the engine that's on this side. Because if I start firing it, then the ship is rotating, my whole ship is going to start tumbling end over end, and I'm going to have real problems navigating. Okay? So you'd have to either stop the rotation, which would eliminate your gravity, or you'd have to have some sort of computer program that's perfectly timing all the motors at various times to fire and maneuver. Okay? So there's some practical problems with having just a big wheel. Now, if it's a satellite, it doesn't matter as much. Okay? Once you get it into orbit, you don't really have to do much else to it. You could just have a big wheel in orbit. Okay? And this idea, like I said, has been around for a long time. How many people have seen Arthur C. Clarke's 2001 A Space Odyssey? It's a very old movie. It's even older than me. Okay? But it has kind of stood the test of time because a lot of the special effects in it were at the time very groundbreaking. Okay? And so they look, even by today's standards, pretty decent. Okay? And this was all pre-CG. And this was like the late 60s. Okay, that this movie was made. In fact, George Lucas stole a lot of the stuff from it too, okay, to do his special effects for Star Wars. But the idea is that the movie was based on a book written by Arthur C. Clarke. Arthur C. Clarke was an astrophysicist, okay, who then ended up being a science fiction writer. Made a lot more money doing that than he ever made as an astrophysicist. Okay? So he had all these ideas that actually have come to fruition, oddly enough. Over the course of time. Not by 2001, most of them, but okay, eventually they have. So we're going to kind of look at what this looks like in terms of, like, in a science fiction movie, the practicality of it, and how they filmed it. And because actually making this set work was a real trick. And because for the movie, they actually had a set that rotated, and the actors were inside of it, and they filmed it as it rotated, which is tricky, because where are the actors when they're filming this? What planet are they on? Earth, where there's actually gravity. But they're supposed to be in a spaceship where there's no gravity, but this thing is generating artificial gravity. So it was basically a hamster wheel. Okay? And they just always filmed the actor at the bottom and the set rotated. So if he was walking, he actually just did this and the set rotated, but they made it look like he was walking around the ship instead of the ship rotating with him in it. Okay? The only trick was when there had to be more than one of them in. So he'd have to seatbelt himself in for when he was upside down, and the other guy's walking on the bottom, otherwise he would fall. You never notice it's totally seamless. Okay, but I'll show you some of the stuff, and also the big rotating space station idea that they had here. What we're going to look at here is how do you pull this off? Okay, so if you're standing here, you need to feel a force against your feet directed back towards the center that acts as a centripetal force. That force is going to be the normal force of your inertia pushing against the drum and the drum pushing back. Okay, what do we want that force to feel like?
Gravity.
We want it to feel like gravity. So essentially, all artificial gravity questions break down to the centripetal force equaling the normal force, which we want to feel like gravity. Okay, so there's really not much to an artificial gravity problem except to remember that you want it to feel like gravity. So you have mv squared over r equals m times g. Okay. What's going to happen to the m's?
They're going to cancel.
Yep, they're going to cancel. Okay, and they're going to cancel because it doesn't matter what my mass is. If I'm standing in that spot on that space station, I'll feel like I'm at home on Earth. Okay, because it's only based on the acceleration that I feel. Okay, my mass makes me feel my weight. Okay, someone else's mass makes them feel their weight. Right, but everybody feels the acceleration due to gravity the same. All right, everyone okay with that idea there? Okay, that's all that an artificial gravity question breaks down to. That's like, you can just remember that, because I almost always put one on the test. Okay? Artificial gravity, centripetal force equals gravity on Earth.
Artificial gravity couldn't work here. Like you couldn't do that with the spinning thing here. No, it would have to work in zero.
Well, the gravitron works that way.
Right.
Right? So it works, it's just not practical.
Right. Like,
Right? It wouldn't be quite the same, because you'd still have that gravitational
like
field.
in zero gravity, could you have a different speeds where it'd be like less than 9.81 and more than 9.81?
Totally. So if you were headed to Mars, you might make the gravity in the spacecraft, initially like Earth, just for health reasons. But then as you approach Mars, you'd probably back it off to Martian gravity so you could get used to Martian gravity, right? And then on the way home, so you look good at the beach as a superstar. When you get home, you crank it up to 1.5, 2 G, so you can get really jacked by the time you get home, okay? Under 2 gravities. Something, I don't know. It just depends on how fast you make it spin, right? The faster it spins, the heavier everyone inside feels. Okay, so that was the idea, okay, that we saw there. Okay, this is just another scene from that same movie where they're both walking together. You can never have a shot, and there never is one, where one of them's walking on one side and one of them's walking on the other. Because one of them would be upside down and falling, okay? But they can walk side by side. All right, so that guy, he came out of the hatch, okay, right here, and he came down that ladder. As he came down the ladder, he'd feel heavier and heavier, okay? When he's in the tube, he's weightless. But as he comes down the ladder, and you could kind of see there, like his legs kind of shot out weirdly until he was able to kind of bring himself under control and get his foot on the rungs of the ladder. Once you're on the ladder, as you come down, you get heavier and heavier. Okay. So let's do this sample problem. Let's say we're talking about the big wheel space station we saw there at the beginning of the clip. Okay? It has a radius of 1,700 meters. Okay? So it's really, really big. Okay? How fast does it have to rotate in order for an astronaut to feel like they're at home. Okay, so normal Earth gravity. Okay, so as we said then, the centripetal force is being provided by the normal force that is resulting from the person inside wanting to leave the circle. We want that normal force to feel like gravity on Earth. Okay, so we can just expand it out to this. Okay, now I'm trying to solve for V, so I got to multiply both sides by R, and then divide both sides by M.
I thought we could cancel out that. Oh, we can't cancel.
Yep, and so M will cancel. All right, that solves for V squared. So what I end up with here is that V equals the square root of GER, G times R. Okay, it's a pretty simple formula. There's not much left in it by the time we get down to it. And that's why we said the theory behind artificial gravity is very easy. It's very straightforward. It's the engineering of making it actually occur that's complex. Okay. So we would have 9.81 times the radius, which we were told was 1,700 meters. Okay, the outside of that space station is whizzing around at 130 or 129 meters per second. Is that pretty fast? I wouldn't want to be trying to perform maintenance on the outside of that. Okay? Like, you would want to crawl down the thing or come out of a hatch maybe or something, okay, on the outside of that ring, as opposed to try and match up with the ring from the outside, okay, because you'd have to go really fast. And what's the real danger if you're doing something on that ring, on the outside?
Let go.
Yep. If you let go, you are going to fly off in a straight line tangent to the circle at 129 meters per second, and there is going to be nothing to stop you. Okay, I would imagine that would exhaust the fuel in your suit jets, trying to even just slow down, okay, from a speed like that. So you definitely want to be tethered. Now, what if you're tethered and you let go?
Gonna start.
Yeah.
You're gonna go.
Yeah. You're going to feel real heavy, depending on how long that tether is, because you're going to be at the end of that tether, getting swung around like that roll of tape on my ghetto physics demo. Okay, like how do you think that roll of tape feels when I'm whirring it around? That's how you would feel, okay, if you were attached to a tether and hanging on for dear life from the outside of that ring. Okay, so it would be certainly quite difficult to do anything. If they were going to perform any serious maintenance, they would probably have to stop the rotation, okay, for safety reasons. Anything on the outside of the ring. Okay, making sense there? So not like a mathematically challenging problem at all.
So I know when we're like standing on Earth, it's a pull of like 9.81 meters per second squared. Right?
Mm-hmm.
But is there a point where like when you get higher and higher, it gets less and less of a pull?
On Earth?
Yeah.
Yes.
Or is it just like goes from 0 to 9.81?
No. In fact, 9.81 is an average.
Right.
Okay, and we'll talk about this a little more when we talk about like gravity and gravitational field strength, but the Earth is not perfectly round. It's not flat, because that's crazy, okay? But it isn't perfectly round either, right? So it's kind of like, that's a big exaggeration even, okay? That it's not a football, but it's not a basketball either. Okay, it's kind of like if someone took a basketball and just squished it a little bit, okay, and like just pushed on the edges. Okay, or it's not perfectly round. So that means that here at the equator, you are farther from the Earth's center than you are if you stand at the North Pole. Okay, so you're actually heaviest at the poles and lightest at the equator. Okay, that sort of makes sense. Now, would you be lighter if you stood on top of Mount Everest than at the equator?
Yes, you'd be lighter.
That's what we would think, right? Because Mount Everest is the highest point on the Earth's surface that you can stand, right? Intuitively, we would think, oh yeah, that would be where I'm furthest from the Earth's center. Except that Mount Everest, latitude-wise, is like probably right about here. okay? And because the Earth's not perfectly round, you're actually further from the center of the Earth standing in the ocean at the equator than you are standing on the top of the world.
Now, if I was in a plane and I jumped, like, would I feel lighter on a plane? Then
Well, most passenger aircraft fly about the same altitude as Everest. It's not noticeable. You would never, ever be able to detect the difference. Okay? We're talking like accelerations go, I think the lowest one on Earth is like 9.77, and then the highest is like 9.83 or something like that. Don't quote me on that, but it's not a huge variance.
Okay. Well, like, so if I'm in a spacecraft and I'm coming back down to Earth, what does it go from, like, does it start just speeding up as you get closer to Earth?
Yeah.
Oh, okay.
But it's an exponential change. Okay? The formula that governs it is this one. This is the other way we calculate the force of gravity. This is a shortcut. This one that we've been using all along, it's a shortcut. Okay? This is the formula I use if I don't know that.
Right.
Okay? So based on, sorry, that's supposed to be square. Okay? Based on your distance from the center of the Earth, you have a certain weight. So this would be the mass of the Earth, and this would be your mass, and then this would be your weight. Okay? So the further away I get from Earth, I'm going to be exponentially less attracted to the Earth. Okay, but we'll learn more about that when we talk about actual gravity, Newton's gravity laws. Okay. All right, so that's what we just did. Okay, so there's lots of ideas. Arthur C. Clarke actually played with this idea in a whole bunch of his books. So if you've ever had a chance to, or you ever get a chance to, Arthur C. Clarke is a good science fiction writer, and he's got several different books where they use spinning drum. In fact, one of his books is about this cylindrical spacecraft that comes to Earth from another civilization, and the whole inside of it is habitable, okay? And it just spins around and around. It's got lights, so these would be lights that act as suns, okay? And plant life can grow on the inside of it, and there's real gravity, okay, and all of that stuff. There's just a couple of problems with being in a cylinder, okay? When the cylinder wants to accelerate, what happens to everything inside the cylinder? Is it going to feel that? Okay, give you an idea. Part of the design of this spacecraft looked like this. So I'm just going to draw a rectangle so that I've kind of got part of the spacecraft here. Okay? So in the middle of the spacecraft is what they call the cylindrical sea. It's a big body of water in the middle of the spacecraft. On one side of the spacecraft, okay, so this would be the back where the engines are, okay, and this would be the front. Okay, so in the front of the spacecraft, the cylindrical sea has a cliff that's about this tall. The back of the spacecraft, the cylindrical sea has a cliff that's 10 times taller. Why? So the water level in the cylindrical sea only goes about this high when the spacecraft is traveling at a constant velocity. What happens to the ocean when the spacecraft tries to accelerate? Yeah, it goes back. It's Newton's first law, right? Okay? If the spacecraft suddenly tries to accelerate, the water tries to sit still. And so it gets sloshed up onto this big cliff. To keep it from sloshing over the cliff and destroying everything on the other side, they need an exceptionally high cliff at the back of the spacecraft. Okay? If the spacecraft wants to decelerate, they flip the spacecraft over and fire the engines, and the same thing happens. The water tries to keep going, and it sloshes against the big high cliff that's on the engine side of the spacecraft. Okay? So they have to build it to account for all of Newton's laws. Okay? It's like, if you have a physics background, even just high school physics, reading that book, you appreciate it on a whole different level than someone who doesn't, because all these things make more sense.
Don't they do that same thing at the end of Interstellar? And a big round thing?
Big round. Oh, yeah. Yes, yeah, the spacecraft that they were using, very similar, yeah, same idea. And they had the shot from downtown there, right? Those kids are playing around on that thing that's down by Heartland Cafe. Yeah, if you've never noticed that, if you ever watch Interstellar, you can pick out lots of local locations. Okay, there's shots from the Dog Stadium, there's shots from that little thing that's down by Heartland Cafe, there's shots in Nanton, shots in High River, Chain Lakes is in there, there's some stuff down Highway 40, okay, that's all shot. Lots of it was shot here. Longview, yeah, the school that his kids go to is the Longview School that you drive by. Okay, cool. Okay, so does that sort of make sense why we would do that? Normally, the water stays put, right? If it's spinning around and around. So this would be the weird thing. If I'm standing in here, I can look up and see water above me. And it's not falling. Okay? Nothing would fall. Okay? Because it's being pinned to the inside of the cylinder no matter where it is because of the cylinder's rotation. Okay? Now, here's the other thing that can be worrisome. If I have this big ocean in the middle and I want to change the gravity, okay, I have to change the spin of the spacecraft. What might I create in this ocean if I change the spin? A tsunami, yeah. Okay. If I suddenly change the spin, I impart some force to the bottom of the water that I don't impart to the top, in the same way that an earthquake pushes on the bottom of the ocean and causes a disturbance that can travel inland. Okay, so you get a big wave. Okay, it's another one of the things that happens.
Wouldn't it be the same as Earth? Because don't they say Earth's spinning too? Is that what's also keeping us on Earth? Is 'cause
No, the Earth's spin has nothing to do with gravity.
Oh.
The Earth's mass is what produces gravity. Besides, we're standing on the outside. If Earth was spinning and this was the same way, it'd be throwing us off.
Right.
Yeah, right? Because we'd have
Then
to
how
stand
are
on
we
the inside.
staying on Earth if it's spinning?
Here's gravity.
Yeah, because of the Earth's gravity.
As a pull.
Yeah. Gravity isn't caused by the spin of the Earth. It's caused by the mass of the Earth.
Right.
Okay. That formula I showed you there before, this one here. Okay. Gravity is an actual mutual attraction between two masses. So this is going to be weird, but the Earth is just as attracted to you as you are to the Earth. It's a mutual
So is
attractive
that the same
force.
thing as if you put like a big heavy thing on a trampoline, and then all those things are attracted towards it? Is
Yeah.
that- It's like, oh.
Yeah, whichever thing creates the biggest dip.
Yeah.
Yeah, it's a good simulation of gravity. Yeah, the bigger the mass, the more things are attracted to it. Yeah, exactly. Okay. All right, that's it for artificial gravity. Where are we at? 9:41. Okay.